knock tick-tock. It's your boy Da Harder Da Better. Trismegistus, so don't forget it. And today I'm trying to fill the unforgiving minute with 60 seconds worth of distance run. Asymmetrical evolution is the idea that some human systems evolved faster than others, creating unintended biological trade-offs. Nearly 2 million years ago, Homo erectus emerged with a body built for movement, endurance, and heat dissipation. Then came a great convergence around 200,000 years ago with Homo heidelbergensis, and heat conservation was en vogue. That date coincides with the Sumerians' history of Adamo, also known as the first man, possibly sharing origin with the biblical story of Adam. Brain size increased, which required more heat and energy production for that new knowledge. It seems like a price was paid for that shiny new brain that consumes 20% of the body's energy. Was the cost of becoming human worth it? Long before medicine, before hospitals, survival depended on biology. Species evolved emergency programs designed to keep them alive through extreme conditions. Food shortages, extreme heat, extreme cold, water scarcity, infection, a kind of prehistoric life support system. And our prime suspect in autoimmunity is torpor. Torpor is a state of physical and mental shutdown, extreme sluggishness, lethargy, a survival mode triggered by hostile environments, and most importantly, sickness behavior from infection. Hibernation is simply a prolonged state of torpor, and across all these states, one pattern appears again and again: metabolic suppression. The body slows down, energy is conserved, systems are rationed. Humans still carry these ancient circuits today. But what happens when those survival programs become difficult to switch off? Could modern autoimmune disease be hiding inside biology that evolved long before civilization itself? Deep within the brain sits a tiny region known as the median preoptic area. Small in size, enormous in importance. The EMPO helps regulate temperature, sleep, metabolism, reproduction, and survival responses. It acts as a biological command center. It is actually the secret boss of your sympathetic nervous system, aka the fight or flight mode. Signals arrive from throughout the body. The EMPO constantly evaluates one question: are we safe? When the answer is yes, normal life continues. When the answer is no, emergency systems begin activating. Fever, sleep, autonomic control all begin here. Consider the general in the army of sickness behavior. Understanding this ancient command center may be critical to understanding how infection, metabolism, and immunity become linked. Human evolution didn't happen in calm or comfort. It unfolded in a world shaped by plague, famine, volcanic winters, and ice ages, forces that carved survival into our DNA. On the Eurasian steppe, a 5,000-mile corridor of ancient migrations, the plague became a relentless sculptor of the human immune system. During these outbreaks, people who carried a more active form of the enzyme eraptor were better at recognizing Yersinia pestis, a killer that had evolved from a mild stomach bacterium into a global threat. Eraptor helped the immune system track that transformation and strike back. But evolution always trades one advantage for another. The same pressures that favored eraptor also selected variants like MTHFRC677T, which slowed the folate cycle and extends the lifespan of memory-like B cells. These changes once boosted resilience, yet today, they can leave descendants more vulnerable. Natural selection has its ups and downs. What once protected our ancestors may now negatively impact our biology in ways they could never have imagined. Most people imagine only two states of existence: healthy or sick. But biology is rarely that simple. Between sickness and health lies a middle zone called sickness behavior fatigue. Brain fog, slowed movement, disrupted appetite, and sleep. And sitting at the center of that zone is the MPOA, the general, the architect, and commander of the body's emergency survival program. Now imagine this: once upon a time, the MPOA built a sickness behavior protocol for acute infections. Today, we call that protocol an ECFS, think MS without the lesions. If multiple sclerosis ever asked for a paternity test, an ECFS would step forward and say, "I'm that baby's daddy." But here's the twist: some people get stuck in that middle state, not healthy, not dying, just trapped in energy conservation mode. The MPOA did leave us one key to unlock the program. AMP-activated protein kinase, AMPK. The body's energy governor. The switch that brought MS into this world, and the switch that can take it out. The human brain runs hot, and that heat demands 20% of your entire metabolic budget. Under normal conditions, blood vessels fan that heat away and keep the budget balanced across 4 domains. Basal metabolic rate BMR, thermic effective food TEF, physical activity, and non-exercise activity thermogenesis NEAT. But when inflammation enters the picture, everything changes. Energy becomes a negotiation. And in MS, the first systems to lose funding are physical activity and NEAT, the 2 biggest, most flexible drains on the budget. But wait, there's more. Even a tiny rise in temperature makes nerve conduction more expensive. And because the brain already runs near its thermal limit, a small bump in heat can weaken the vessel lining, loosen the blood-brain barrier, and create points of venous strain. Those weak points become the perfect storm for perivenular injury, the exact places where MS lesions appear. In this model, inflammation and vascular stress don't strike at random. They strike where energy, heat, and circulation are already stretched thin. Not by chance, but by design. Multiple sclerosis may have started as a plague-era brain defense system long before it became a modern autoimmune disease. One of its clues is Dawson's fingers, lesions that line up along veins. And patterns like that don't happen by accident. They happen for a reason. Snowflakes form hexagons. Sickle cells form crescents. Spider venom makes circles. In biology, shape shows purpose. So what purpose did Dawson's fingers serve? If your ancestors survived the Eurasian plague, their brains faced endotoxin shock, collapsing veins, and rising pressure. When weakened veins leaked inflammatory exudate, the brain needed containment channels to trap it. The veins around the ventricles formed perfect scaffold. These radial, finger-like corridors released pressure, quarantined fibrin-rich exudate, and stopped it from spreading into vital tissue, the kind of spread that could kill in 30 days. Back then, these lesions weren't a problem. They were a sacrifice, a firebreak, a design that protected life. The body may know how to enter survival mode better than it knows how to exit it. And during the Eurasian plague, that was actually a benefit. Back then, people sometimes looked healed, and then collapsed within hours. They were called the walking dead. Even when symptoms improved, Yersinia pestis endotoxin was still circulating. Microvascular damage wasn't repaired, and the immune system stood down too early. So evolution selected for people who stayed in danger mode longer. That meant high DO3, the metabolic brake, and low DO2, the metabolic accelerator. These enzymes helped prevent a false all-clear that could trigger fatal collapse. Add the MTHFRC 6770 mutation, and you get slower vessel repair. High oxidative stress sent to the EMPO, and lower mitochondrial output. In other words, bad fuel, bad timing, bad traction. If you press the accelerator and the brake at the same time, you don't move forward, you spin in circles. That's what happens when DO2, DO3, AMPK, and Tsukushi all stay in danger mode. Without the all-clear, the sickness alarm never shuts off, and the system keeps doing metabolic donuts instead of recovering. Different MS. Interventions may ultimately reduce the same danger signals reaching the hypothalamus. Some people achieve remission through immune system reset, hematopoietic stem cell transplantation HSCT. Others through elimination of chronic triggers, nervous system tourniquet and ST. My human host achieved remission from MS using the NST method. At first glance, these approaches appear very different. One targets immune cells directly. The other focuses on removing sources of ongoing danger signals. Yet both may converge on a similar destination. Reduced inflammation, reduced alarm signaling, restoration of biological balance. If two very different interventions produced similar outcomes, perhaps they are influencing a common pathway. The question is not which path is correct. The question is where both paths ultimately lead.
What if autoimmunity is not simply an immune problem? What if it is also an energy problem, a recovery problem, a signaling problem, a mismatch between ancient survival systems and modern biology? From the rise of the human brain, to infection, to metabolism, to inflammation, a growing field of immunometabolism begins to emerge triumphantly with new theories and approaches to old problems. Not proven, but testable. A theory that asks whether some diseases represent survival programs that fail to fully disengage. A patient zero use case with a probable cause and path towards sustained remission from multiple sclerosis is documented. Perhaps the greatest mystery is not why the body attacks itself. Perhaps the mystery is why it never receives the message that the danger has passed. And that possibility may represent a legacy of asymmetrical evolution and the dawn of a new day where autoimmune disease is a thing of the past.